In this last video, we're going to finish off Chapter 13 material and look at some different methods that people have come up with to test the effectiveness of these different kinds of treatments, because when you look at this, you want to be able to have some way of measuring how effective these are so that you can know the limitations, but also when you should use certain kinds of techniques and why one would be better than the other. So again, this is one of those things where I want you to consider the advantages and disadvantages to these different kinds of treatments, but also their limitation. And one of the first methods that people came up with is what's known as the phenol coefficient. And this method is not really widely used anymore because it was kind of arbitrary when they set up the conditions, because they're looking at the bactericidal activity of a chemical relative to phenol. And one of the first questions is, well, why look at phenol? And really it's because this was one of the first chemical disinfectants that was devised when you go all the way back to Lister back in the mid to late 1800s. He started using phenol as an antiseptic to treat surgical incision sites and also on a lot of dressings that are out there. So that's one of the historical sort of reasons why people will compare this. Will compare the activity of their chemical to phenol. And effectively what you do is you take your test cells and you dilute them or you put them into a test tube with your chemical that's diluted in water, and you let it sit there for 10 minutes. Why 10 minutes? Because that's what somebody decided on doing to keep it a standard thing. And then you take that and you plate some of that solution with your cells onto your culture media and spread it out. And then you effectively look at the number of surviving cells. And what you're doing with this is you can use it to identify the concentration of the chemical that's needed to kill your cells. So you can set up a dilution series of your chemical and basically say, what's the minimum amount of this, or how many times can I dilute it before it is no longer effective at killing off my cells? So again, we're looking at bactericidal activity. And then you will calculate this as the highest dilution of the chemical that kills in 10 minutes compared to the same ratio that you would have for, or the same dilution that you would use for phenol. And so again, it seems like it's kind of arbitrary, but effectively what you're looking at is if your coefficient or your ratio of this chemical to phenol is greater than 1, then you know that your chemical is more effective than phenol. And if it's less than 1, you know it's less effective than phenol. So there is the ability to look at the effectiveness, but remember, if we looked at these different chemicals, some of them are going to have different modes of activity, and they aren't always going to be having the same method or the same mode of action as what you would have for phenol. So again, it's kind of an arbitrary method that isn't as reliable as people would like to think. One of the more widely used methods that's out there is the disc diffusion method, and this is where you will take your chemical and soak it into a disc and then place that disc onto your lawn of freshly smeared cells on an agar plate, and then that chemical diffuses out from the disc, and as it diffuses out, you're going to see a lower and lower concentration of your chemical, but you come back the next day and you measure the size of the zone of inhibition around there. So this is great. It lets you know whether or not your cells are inhibited by the chemical. It isn't necessarily measuring whether or not it's cytal. It's just telling you that you inhibited the growth of the cells there. And the size of your zone of inhibition does not reflect better killing power. What the size is really just an indication that this chemical diffused really far, and even at low concentrations, we can still get an inhibition of growth there. So your size does not correlate with more killing power. So you do have to be careful of your interpretation, but at least you know that this chemical at a certain concentration is able to actually interfere with the growth of your cells. Something like a tincture or just using straight up alcohol on these plates does run into problems because remember, alcohol can boil at room temperature. So if you put your plates at 37 degrees when you're testing something like E. coli, your alcohol is not going to be around long enough to effectively interfere with the growth of those cells. So you might get no zone of inhibition around your disc that's saturated with alcohol. Another method that we can see is what's known as the use dilution test, and this is sort of the standard industry method for measuring how much dilution can I use with this chemical and still have it be effective at disinfecting an area. And they wanted to standardize some method of getting it so where you're sort of mimicking using this on a surface. And so their solution for this is to actually take some metal cylinders and dip them into some culture media with your cells, and then take them out and air dry them. And that's going to give you some cells on the surface of this. So kind of mimicking like a desktop that you're using where you're spraying your disinfectant there. And then you will take these discs, or these cylinders rather, with your cells on them and then soak them in a test tube with your solution of disinfectant. And again, you can use different dilutions of your disinfectant, and you let your cells sit there for 10 minutes, kind of similar to our phenol coefficient experiments. But then the big difference is you take that little metal cylinder out of your disinfectant solution and you transfer it to a fresh tube with some sterile culture media and you incubate it. If your culture media turns turbid or cloudy, then you know that your cells survived and that that particular dilution in 10 minutes was not enough to actually kill things off. If you don't see any turbidity, then you know that your organism was actually killed by the disinfectant at that dilution in 10 minutes. So this can really be used to test not only the use of it, but also what is a proper dilution to use for your chemical to actually kill off your target organism there. The last method is a little weird when we consider what it is, because this is what's known as the in-use test. And what you're doing with this is basically determining whether or not the disinfectant is still working, especially if you're using this in something like a clinical setting. So maybe you're running into some problems with cross-contamination, or a lot of infections are occurring, and you want to see, is my chemical actually contaminated with something? And so what you do with this is you take your disinfectant right here and you dilute it into a sterile broth solution right there. And then you will take and put 10 drops onto 2 different plates, and one of those plates will be incubated at elevated temperatures for 3 days and the other one at room temperature for 7 days. So that 37 is to mimic body temperature for humans. And then you take a look at the growth of these things after those incubations, and if you see more than 5 colonies, then you do use that as your measure and say this is contaminated. And for me, the problem with this is, okay, yeah, I had viable cells in my disinfectant, but it's 7 days after I started testing it, so wouldn't it be easier just to throw out the disinfectant and get some new ones? That probably works with a bottle, but what if you've got gallons and gallons of this stuff that you're looking at and you want to test whether or not it is contaminated? So that's really where you're going to be using this in-use test. And then the last thing that I just want you to consider is to take a look at all of these different kinds of active ingredients that are included in commercial antimicrobial products. So you can see your Lysol and your Clorox disinfecting wipes are going to have these little quaternary ammonium compounds in them. Your halogens in these mildew removers, those are going to be great at penetrating through the fungal cell walls and oxidizing the cells that are out there. And here we can see Triclosan, which is a phenol-based compound out there that is being added to hand soaps that are out there. And if you look, you can see it's in Noxema, and it's also way down here in Colgate toothpaste. Well, if we look at all these things and think about, these are stuff that are coming in contact with our bodily tissues. If you're using it in your toothpaste, there's a chance that you could be swallowing this antimicrobial product that is included to try and reduce the number of microbes. But what effect is this having on us in the long term? And if we look at this little graph over here, what you can see is a comparison of the number of bacteria in the scrub water. So you wash your hands over a basin and you collect that water, and then you put some of it onto an agar plate and you count the number of colony forming units, which gives you the number of cells that are in the scrub water. Well, look at this. This is millions of bacteria per liter. After 1 day of incubation, we can see that you've still got a pretty good number of cells, and when you really start to see the drop off is after 2 days of incubation. So this germicidal soap, so think dial antibacterial soap, did not have an immediate effect on the growth of those cells. It took a few days for this to actually have an effect there. This is not working immediately. It might reduce the load at the beginning, but it's not certainly germicidal where you're killing off a massive number of the cells all at once, which is what people tend to think is going on with these germicidal soaps. And if you look at this, Triclosan has been found in the urine of 75% of Americans who were tested. It's in the urine, which means it must be getting ingested, it's going through the bloodstream, and it's getting processed by your kidneys, and that's how it's ending up in your urine. We can find detectable levels of this chemical in groundwater sources that are out there. So you are drinking this stuff potentially. You're not just getting it from brushing your teeth, it's in your water. And when you expose this chemical to sunlight, it actually creates what are known as dioxin-like compounds, which are carcinogens. These have also been found to affect the endocrine system. And there is a study in Germany where they were actually able to show that triclosan exposure looks like it's causing a change in the sex of frogs that are living in contaminated water. So it's actually causing their hormones to shift, and you will see the male frogs are actually losing characteristics of maleness, and they are becoming more female-like as it is interfering with the hormone signaling in their endocrine system. But really the biggest worry is, if you think about this, people using this chemical at home, those are selecting for resistance. And the more resistance you develop in the public, the less likely we are to be able to use these kinds of chemicals in the hospital. So we are actively selecting for more resistant pathogens at home, and then somebody goes to the hospital and they spread them around, but we can no longer disinfect the hospital area because the cells have already developed resistance. And there is this idea called the hygiene hypothesis that postulates that this increased use of these antimicrobials in households is leading to an incidence in allergies, eczema, and asthma in children. And so the idea is that we should normally be challenging our immune system with organisms that are constantly we're being exposed to. They're landing on your skin, you're breathing them in, you're eating them and drinking them, and that if you disinfect everything, your immune system is not getting worked out. So you're becoming a couch potato in your immune system, where you should be getting up and exercising your immune system by constantly challenging it. So this hygiene hypothesis is in our ability to try and make everything cleaner and more disinfectant, we're actually resulting in more damage to ourselves.